welcome back to another episode of the Phosphorus podcast, your go to source for unraveling the mysteries of phosphorus and its impact on our world. I'm your host, Jihan Zian, and today we have the privilege of diving deep into the realm of phosphorus and fertilizer technologies with a distinguished guest, Rob Norton. Could you please introduce yourself to our listeners and tell us a little bit about your background and your international experience?
Thanks, Jane, for having me here. And my name's Rob Norton. I'm a consultant who's worked across a few international areas. My background is as a field agronomist. My PhD was on canola agronomy, and that was in the 80s and 90s in Australia. And I worked for the University of Melbourne, teaching crop science, agronomy, some soils. Had a small research group based at Horsham, which is in the southern Australia, halfway between Melbourne and Adelaide. And after that period, we had some great research projects, which we might talk about later. I moved to work for IPNI, the International Plant Nutrition Institute, from 2009 to 2017, when I retired from that organisation. And since that time, I've been lucky enough to visit Morocco, working with my colleagues in APNI and at UM6P, and now more recently at the Global Phosphorus Institute. So I've been very lucky to visit some places across the world, including Morocco.
As a field crop agronomist, how important is it for a farmer to pay close attention to phosphorus management?
It's interesting to talk about how important phosphorus is. In Australia, our cropping industry started to develop at the turn of the end of the 19th century into the start of the 20th century, and a key part of that was the adoption of phosphorus fertilizers. And the research that was done came from the UK, from England, from places like Rothamsted, and farmers really were careful and used a lot of good information to help use phosphorus effectively. And crop yields responded very well, because many of our soils are quite old and heavily weathered, and phosphorus levels are low. And that continued for quite a while until what we called the sub and super era. In the 50s, there's a big demand for wool, and a lot of our grazier farmers who grew sheep for wool, needed to improve their productivity, and using subterranean clover as the base and superphosphate as the fertiliser, productivity increased dramatically. And not only for the pastures, but also that improved fertility, nitrogen and phosphorus fertility, flowed into the grains industry. And more recently, we've seen the development of industries like canola. And canola in 1990 was maybe 40,000 hectares in Australia. It's now our third biggest grain crop, 4.5 million hectares. So it's a very big industry, and a lot of that has been due to the capacity of growers to understand best practice phosphorus management. Soil testing is fundamental, getting the right rates and the right times and the right place for our nutrient stewardship, and the right source. So phosphorus has been fundamental to the development of our Australian agricultural systems.
You've done some interesting work with Free-Air Carbon Dioxide Enrichment. Can you explain what that involves and why is it important?
One of the research areas I worked on when I was at the university, and even continued some of that work into my time at IPNI, was we established a free-air carbon dioxide enrichment experiment, which we called AGFACE, AGFACE. And that aimed to make an assessment of how elevated carbon dioxide would play into crop growth and yield, and not just cereals. Initially we focused on cereals, but later did work on legumes and oilseeds, and some pasture species as well. So AgFace was the way it's designed is we basically fertilise the area under study with extra carbon dioxide. So we blow carbon dioxide across the growing crop, the crop's growing in the ground, and we make whatever measurements we need to make for the experiment. And that might be obviously crop yield, grain quality, crop growth, potential for pests and diseases, varietal differences, differences in fertiliser management, phosphorus and nitrogen. And we did that work, that series of experiments continued over 13 or 14 years, and we recently published in Advances in Agronomy a summary of all that work, and I'll recommend if people want to find out more about that. But the bottom line is that we found that carbon dioxide does increase crop growth, does increase grain yield. The numbers we had were about 20% if you had 550 parts per million carbon dioxide. Present, it's about 400. So that level was chosen to be something like 2040 or 2050. Hopefully we don't get to that, but the trend is yes, we will. We wanted to understand how that crop increase would play into, in particular, grain yield, but also grain quality. We found that one of the things that we particular interest was the effect of elevated carbon dioxide on grain protein. And unfortunately, grain protein declined with higher yields because the plants were less carbon inhibited and more nitrogen inhibited. And that was quite an important issue. We think there are some genetics we can use to address some of that. We also found that zinc declined under high CO2. And zinc is very important for human nutrition, very important for children in particular. So there are some positives, but there are also some negatives. And there's also implications in terms not just of elevated carbon dioxide, because climate change comes along with lower water availability and generally higher temperatures, more variable climate. And that requires us as farmers and advisors and researchers to really be careful with our inputs, manage our crops in maybe different ways, more opportunistic ways, and also look for new genetics to help us overcome some of those limitations like protein and zinc declines.
What are the consequences of increasing levels of CO2 in our atmosphere?
So CO2 increasing in the atmosphere, obviously, as we've mentioned, has some impact on plants in terms of carbon dioxide fertilisation effect. But carbon dioxide also plays a role particularly in climate change. It is greenhouse gas. It stops heat escaping from our surface, from our atmosphere, and so the climate warms, the climate gets more energy in it, and a consequence of that, it's not just getting hotter. We find that things in Australia, in particular, in those southern latitudes, maybe 25 to 40 degrees south and 25 to 40 degrees north, those sort of latitudes, variability becomes much greater.
As we all know, climate change is impacting agriculture for good and bad around the world. Do fertilizers have any impact on climate change, and can fertilizer aggravate or mitigate climate change? How can nutrient management affect greenhouse gas emissions?
I think one of the phosphorus, as I said, is fundamental to our farming systems, has been and will continue to be, simply because we remove phosphorus in the products and take it out of the field. And so that phosphorus has to be removed to maintain soil fertility. There are technologies looking at how to improve phosphorus use efficiency, and I suppose a fundamental part of that is to make sure that other nutrients don't inhibit the use of phosphorus. So, making sure the micronutrient status is okay, nitrogen is adequate, soil pH is good, acidity, salinity, all those things can reduce the effectiveness of phosphorus fertilisers. There are some technologies around with coatings of phosphorus that are still being developed and still being evaluated, and I would hope that the technology in fertiliser manufacture will keep making these assessments and hopefully identify something that can help improve phosphorus efficiency. But it still goes back to the fundamental issue that if you remove phosphorus in the product, you have to replace it with fertiliser. It's not like nitrogen, which you can fix nitrogen from the air. Phosphorus, on a mass balance, input and output, has to at least be balanced.
Nitrogen fertilizers can contribute to nitrous oxide emissions. So, what about phosphorus fertilizers? Does its use contribute to or affect in any way, shape, or form greenhouse gas emissions?
We've talked about how carbon dioxide would increase plant growth, which is fantastic. That's the carbon dioxide fertilisation effect. The issue comes down to more than that, though, because the impact of raising carbon dioxide levels in the atmosphere, and carbon dioxide is a greenhouse gas, what that means is that radiation isn't able to exit from our atmosphere, and our atmosphere warms. Now, warming is okay, but there's more energy in the atmosphere, and the energy, particularly at the latitudes, maybe 25 to 40 degrees north or 25 to 40 degrees south, those areas are likely to become more variable in climate. There's more energy. We in Australia have seen a lot of forest fires. Forest fires are common in Canada and California now. We seem to be seeing more episodic events of climate catastrophes, things like fires and floods and hurricanes, and that is because the greenhouse gas levels are stopping heat getting out of our environment. So that there is a small benefit, but the issue about trying to reduce greenhouse gases in our atmosphere is a grand challenge, and we need to start addressing it. We need to keep addressing it.
Can you explain the environmental concerns associated with phosphorus and can they be managed? Do the environmental impact of phosphorus offset its beneficial effects?
Phosphorus management is an ongoing challenge, there's no question of it. We have areas that are in desperate need of additional phosphorus, Africa in particular, much of Africa in particular. And there are places where there is phosphorus excesses that are causing environmental impacts. So the biggest challenge is to identify and manage those areas appropriately. In the high phosphorus scenarios, the concept of circular economies becomes important. That is where we've got a recovery of phosphorus from manures, from animal products, from whatever source, from wastewaters. Those are the sorts of technologies that can really help. In terms of where areas are low in phosphorus, the greatest challenge is actually identifying those areas. So that's not the big difficulty. The big difficulty sometimes becomes getting phosphorus into those places where they're needed most. Often it's small landholders, and working with them and them working together with science. I think there's a lot going on there. The Global Phosphorus Institute is playing into that very well with the work it's doing globally, and also organisations like UM6P and the African Plant Nutrition Institute also play a big role, along with all the other organisations, particularly working in Africa, to address this low phosphorus status that we find, particularly in the acid soils in the tropics and subtropics.
In your opinion, what are the biggest challenges related to phosphorus and what are the greatest opportunities?
As with anything, if there's an imbalance, whether a low phosphorus or high phosphorus, we can have environmental issues. If phosphorus is low, inputs of phosphorus are low, we reduce soil organic materials because that then contributes phosphorus. If inputs are high, well above removal, we can get phosphorus being moved from where we put it to places that we don't want it to be, such as in waters, whether it's lakes or freshwater or seawater. Those issues have become abundant in Australia because of agricultural production in very high rainfall, sugarcane production areas adjacent to the Great Barrier Reef, one of our great natural assets. Growers are managing phosphorus by making sure that they put on enough, adequate phosphorus and don't over-apply it. It's an expensive input anyway, so it makes very little sense to over-apply it. We do have problems in some of our systems where we have animal systems in particular adjacent to freshwater estuaries and so forth, that animals are not very phosphorus efficient. You have to feed them a lot of phosphorus and a lot of nitrogen for them to grow and grow. And so we do get phosphorus losses in manure and urine. And again, if that's not carefully managed, and it's not just phosphorus, it's nitrogen and phosphorus, we can end up with those nutrients ending up in the waterways. Again, can that be managed? Yes, it can. There's no question about that. The way growers are managing it, say in the wet tropics, and also in the around dairy farms, is to manage water. Phosphorus moves in water or soil, and so reducing soil erosion, managing soil erosion with strips, with vegetation strips adjacent to watercourses, interceptor drains. They're the sorts of, these technologies have been around for a long time, and we really are getting much better at understanding the precise places to put them with GIS, GPS type technologies helping us work through landscape level phosphorus management. Fertilisers have a positive and negative effect on crop performance, and also directly and indirectly in terms of climate change. We know, for example, that nitrogen fertilisers generate nitrous oxide emissions. We also know that there's quite a big greenhouse gas footprint associated with the production of nitrogen fertilisers, mainly because they use coal or gas as the feedstock to produce urea and ammonia type fertilisers. The issue with phosphorus fertilisers is less clear. There's certainly a greenhouse gas footprint associated with phosphorus fertiliser manufacture. But then with phosphorus fertilisers themselves, their stimulation in growth, in some extents nitrogen too, will help capture more carbon. It's fresh carbon, it's new carbon in the atmosphere, it's not old carbon which has necessarily come from fossil fuels. But pea fertiliser, we've seen in our experiments with the FACE experiments, the high carbon dioxide treatments, phosphorus becomes more important for legumes in particular to help them fix more nitrogen. So phosphorus in itself can help offset some of the nitrogen fertiliser demands that would be for our cereal crops by increasing the nitrogen fixation of legumes, provided we have the phosphorus status there to help those crops grow and fix in. Contribution of fertilisers to greenhouse gas mainly come through the nitrogen issue, but as I mentioned, phosphorus does have a footprint. There's a lot of interest in developing nitrogen fertilisers that control the release of ammonia, control the release of nitrate, so reduce nitrous oxide production. We know we've done quite a lot of work in Australia with my colleagues who have identified the potential for nitrification inhibitors to reduce the production of nitrous oxide, and that does represent a technology that can help in managing greenhouse gases. Thanks for the opportunity to talk about plant nutrition. As an agronomist, a field agronomist who cut my teeth on canola and field crop canola, we understand how important nutrition is, as well as good genetics and good crop protection and good soil management. So thanks for the opportunity to talk about it.
We hope you gained valuable insights into the world of phosphorus and environmental stewardship. Again, a big thank you to Professor Norton for sharing his expertise with us today. If you enjoyed this episode, don't forget to subscribe, like, and share it with others who might find it equally intriguing. Stay tuned for more captivating discussions on the Phosphorus podcast.